Section 2 is on machines. Now, a machine is something that eases the load by changing either the magnitude or the direction of a force to match the force to the capability of the machine or the person. So what does that mean in essence? Helps make a task easier. Well, since we're talking about work, using machine, we have two different types of work. We have the work that you do, which is considered to be the work input, or WI, or we have the work the machine does, which is the work output, or represented as WO. Now, as also with work, we have two different forces. We have the effort force, which is represented with FE, force exerted by a person, or we have the resistance force, FR, and this is the force exerted by the machine. If we take the ratio of the resistance force over the effort force, we have what's called the mechanical advantage. Most machines will have a mechanical advantage greater than 1. When the mechanical advantage is greater than 1, the machine increases the force applied by a person. So if you kind of think about it, if you use a bottle opener to take a cap off of a glass bottle, you're not going to, your effort force isn't that great, but the resistance force should be greater. Now, the work input, to find the work input, we take the effort force times the distance the effort force travels. The work output would be equal to the resistance force times the distance the resistance force has to go. Now, one thing to note is that the machine can increase force, but it cannot increase energy. An ideal machine transfers all energy, so whatever the output is also equal to the input work, or WO is equal to WI, or if we rewrite it, FRDR is equal to FEDE. Now, if we kind of get forces all on one side and our distance on the other side, FR over FE, that's our mechanical advantage, is equal to DE over DR. Now, this ratio of DE over DR is our ideal mechanical advantage, or IMA. In a real machine, not all the input work is available as output work. Energy removed from the system means that there is less output work from the machine. Kind of think about that. Nothing is going to work as it should all the time. So what we have is what's called efficiency. Efficiency is indicated with a lowercase e. And this is the ratio of the output work to the input work, so WO over WI. And efficiency is a percentage, so we multiply by 100. An ideal machine will always have 100% efficiency. Real machine will have less than 100% efficiency. So efficiency is equal to WO over WI, which is equal to FRDR over FEDE, which is equal to the mechanical advantage over the ideal mechanical advantage. So what we're going to do today is we're going to look at this problem. An electric pump pulls water at a rate of 0.25 cubic meters per second from a well that is 25 meters deep. Water leaves the pump at a speed of 8.5 meters per second. So problem A, what power is needed to lift the water to the surface? Now I kind of ran out of some space here to show this, so I'm going to do this on a different piece of paper. So some things that we need to know. I can't spell today with anything. All right, so the density of water, 1 gram per milliliter. Okay. 1 cubic centimeter is equal to 1 milliliter. If we look back at the problem that we're dealing with, our volume is in cubic meters. So what we're going to do is we're going to kind of convert over to cubic centimeters to kind of help us out there. All right, so 1 cubic meter. Now going from meters to centimeters, we should remember that there's 100 centimeters and 1 meter. And to cancel out the cubic meters, we would have to cube this whole thing. So that means that we have to cube 100. So if we cube 100, we get 1 million. So we have 1 million cubic centimeters. So if we can use that to get our mass, we can rewrite our density. Instead of saying 1 gram per milliliter, we can say that it's 1 gram per cubic centimeter. And we're going to multiply that by our million cubic centimeters. And we come up with, hopefully you can figure this out in your head, 1 times a million is 1,000,000 grams. Our mass usually is going to be in kilograms, so we need to convert from grams to kilograms. 1 kilogram is equal to 1,000 grams. Grams cancels out, and then instead of putting this through a calculator, we can make this easy and cancel out 3 zeros, so we have 1,000 kilograms. Alright, so now getting back to our problem, it's asking for what is the power needed to lift the water to the surface. Well, from section 1, power is equal to work over time. So we need to figure out the work. Well, we know that work is equal to force times distance. So if we figure out our force, we know that the pump is pulling 0.25 cubic meters of water every second. So our time is going to be 1 second. So we're going to take the 0.25 cubic meters. We have 1,000 kilograms, honestly, per cubic meter. Then we're going to take acceleration of gravity, then multiply by our distance, which says that it's 25 meters deep. Alright, so 0.25 times 1,000 times 9.8 times 25, and we come up with 61,250 joules. Sorry. Alright, so now that we have our work, we can find our power. So 61,250 joules per 1 second is equal to 61,250 watts. Okay, or if we want to work with a little bit easier number, we can put it into kilowatts. So 1 kilowatt is equal to 1,000 watts, so that's 61.25 kilowatts. Okay, so that's A. What power is needed to lift the water to the surface? 61.25 kilowatts, or 61,250 watts. Okay, now B. What power is needed to increase the pump's kinetic energy? Alright, so for that one, let's use this one. All right. So power is equal to work over time. Now, since with this one, since it's asking for kinetic energy, work is equal to the change in kinetic energy over time. So find kinetic energy, that is 1/2 mass times v squared over time. Okay, so one half times, and then we're going to do our fun little calculations that we had to do for the first one. The volume that was pulling up per second is 0.25 cubic meters. We have 1,000 kilograms per cubic meter. So that takes care of the mass part. Now, velocity, V. Back in the original problem, it says that the water leaves the pump at a speed of 8.5 meters per second. Let's scroll that, and that was all over 1 second. So let's put this through the calculator. So 0.5 times 0.25 times 1,000 times 8.5 squared. I'm coming up with 9,031.25 watts. Or if we want to put in a little bit, we can say 9 kilowatts. Alright, so let's look at problem C. It says if the pump's efficiency is 80%, how much power will be delivered to the pump? Okay, so here's B, C. So efficiency is equal to work output over work input. We know what the work output is because that's what we got in B. That's how much power, that's how much work is being done, or power needed. We know the efficiency. So 80 is equal to, then I'm just going to use 9 kilowatts over WI. So find the work input, or power input, excuse me. Let me show you actually how this comes out to be, how I'm knowing this, remembering this. All right, so work output would equal to powered output over time over power input over time. So P over PI. PO is the 9 kilowatts. We're trying to find the PI. So PI would equal to 9 kilowatts over 80, or actually let's put that as the 9,000. So I bet that's what they want to keep it as. So kilowatts, they'll put it as watts. So 9,031.25 over 80. So I already installed that in my calculator, and let's divide that by 80. And I'm going to multiply that by 100. So we get 11,289.6 watts for the input power. The second part of section 2 I will have ready for you on Wednesday morning. Next week I am planning on having a web online meeting to meet with you all so we can go over both assignments and everything before we have a quiz over this stuff. If you have any questions, let me know. And don't forget that the assignment is due on Tuesday, the 14th. Thank you.